Hello everyone, my name is Seung, today's presenter. I'm going to present my research O-AFA, Order Preserving All Flash Arrays for Journaling File System. Here is the outline. Our presentation is divided into 4 sections, each motivation, problem, design, and evaluation. Here is the motivation section. Journaling file system issues two kinds of I/O in order, each normal I/O and commit I/O. Normal I/O is about the modification of data or metadata block. Meanwhile, commit I/O is for indicating normal I/O is written successfully. So commit I/O must become durable only after normal I/O becomes durable. To do that, due to the complexity of current Linux I/O stack, host just wait journaling block becomes durable and then issue commit block. However, waiting on durability means I/O speed is bounded by NAND flash programming speed. In this research, we suggest the scheme that we don't have to wait durability for ordered I/O. We try to resolve this problem by leveraging the property of barrier-enabled I/O stack by Won et al. Barrier I/O preserves order throughout the layer. However, inserting mapping layer to order preserving I/O stack causes some problem. We will explain it shortly. Before we go further, let me explain the definition of epoch defined by barrier I/O. First, I/O within epoch can be freely reordered. Second, I/O between epochs should not be reordered. First problem is that Linux MD shuffles I/O. It results in changing order within epoch. Thus, barrier flag, which guarantee the following I/O becomes durable after barrier flagged I/O, may not be dispatched lastly. Let me take an example. JBD2 issues epoch 1, which consists of data 1, data 2, journal descriptor block, journal logging block 1 to 5, and epoch 2, which consists of journal commit block. Linux MD shuffles order and dispatches the I/O as shown in the picture. Note that there are data 2, journal logging block 5, journal descriptor block, journal logging block 3, journal commit block in the dispatch queue of storage 1. In this case, journal commit block may become durable first, then journal descriptor or journal logging block 3. This may cause the damage to the file system consistency. The second problem is that barrier flag I/O just goes to a single storage. Specifically, if journal commit block goes to the storage which does not receive barrier flag I/O, it can become durable earlier than the other I/Os in the dispatch queue. In our example, journal commit block can become durable faster than journal logging block 1, 2, or 4. Here is the design section. So we introduce epoch in flash array and cache barrier stripe. Epoch in flash array reassign barrier flag. It tracks the start and termination of epoch, and it dispatches last stripe of epoch as cache barrier stripe. Cache barrier stripe is the scheme that dispatch barrier flag I/O to all disks in flash array. If there is no dirty block for the stripe, it creates zero-size barrier I/O and dispatches it. And we introduce commit block stripe to ensure file system consistency. It is all barrier flag and becomes valid only if all commit blocks in the stripe becomes durable. Otherwise, it is invalid. Here is the evaluation section. Our works performs better than ext4 up to 70%. We evaluate our idea using various benchmarks: FIO, BAML workload, and FileBench, OLTP insert workload, and MySQL, inserting transaction at POSIX and while journaling mode SQLite. O-AFA performs better than ext4 by 51% at FIO and 71% better at BAML.